All right. So you're going to be focusing on diodes. There are several different types that we are going to explore in experiment 8. The small signal diode, and I can quickly write the part numbers here. 1N4148. Zener diode is going to be 1N751. The LEDs come in variety of colors, and there is a photodiode that you could use to detect light. And each of these diodes have a specific application. So experiment 8 will be all about looking at each of these types and figuring out how they are useful in certain applications. So we'll start simple. We'll start with the symbol, followed by why do we need a diode, what is the purpose, a general purpose, and then we'll talk about various applications. So as far as the symbol is concerned, you are going to have a triangle followed by a flat line and then the other terminal. So you've got two terminals here that are connected by an element, a two-terminal element that has a triangle on one of its side and a side, flat line on the other side. And the triangle end is the anode or the positive terminal, and the line is the cathode or the negative terminal. And this guy is the positive terminal. And I can denote the current that flows through the diode as ID, and I can also talk about the voltage that is across the diode. I can say maybe VD. So I've got VD to denote voltage across the diode. If I take two voltage probes, one of them on this end and the negative side of my probe on this end, then I'm going to be measuring VD, voltage across the diode. Notice over here, I've indicated that the current through the diode is always going to go from the anode to cathode. And the reason why this happens is we have constructed the diode to exactly give us that functionality, to allow current to flow only in one direction. So diodes basically do that. Diodes allow current to flow only in one direction. So the current cannot go from negative side to the positive side. It can only go from from anode to cathode. Notice this is the direction of conventional current. It is not the direction of a movement of electrons. It is exactly the opposite to that. Now, how do we construct this anode? The diodes. We construct the diodes by using two semiconductors that are differently doped. So we can have a p-type material on one side and then a n-type material on the other side. What does that mean? That means that we are going to have excess amount of holes where there is a p-type semiconductor, and we are going to have excess amount of electrons when there is a n-type semiconductor, and we are going to essentially put them together and apply external voltage. So when we apply external voltage, and as you can see over here in my diagram, I have indicated that I'm connecting the positive terminal to the p-type semiconductor and the negative to the n-type semiconductor. If I do that, what is going to happen? The positive and the holes over here are going to repel, the negative terminal and the electrons are going to repel with each other. And because of that, if there is a intrinsic uh, layer in the middle of these two p and n type materials, it is going to be very, very small, because now all the charges are pushed close to each other. So what we say is the depletion layer is going to be very, very small, or it's going to disappear. When it disappears, it is going to allow current to pass through the diode. And that particular condition, we call that forward biased. So that's forward biased because we have connected the p-type material, or the anode, to the positive end of the voltage supply. And you probably can guess by now what would happen if I switch the polarity of my voltage source. If I switch this polarity, the negative is going to attract positive here, and the positive is going to attract the negative. Because of that, the depletion layer, whatever intrinsic semiconductor layer is in the middle, that is going to become bigger, which means that the charge exchange cannot happen. And we call that region the reverse biased region of the diode. So by simply changing the polarity of the voltage source that you connect to the differently doped semiconductors, we can control the flow of current through the diode. So that's how we are actually, like, that's the physics behind construction of the diode, and how we achieve this particular aspect of current flowing only in one direction. So that's your symbol and sort of a general purpose application. Then we'll get into what are some specific applications that we might be interested in. So let's see. For applications, I could use 1N4148, which is the small signal diode for fast switching. What does that mean? That means that I can switch from this forward biased to the reverse biased region very, very quickly by changing the voltage that is connected to those regions. So fast switching, that can be one of its applications. The other application include voltage regulation, to make sure that the voltage does not change much, even if there is a change in current through the diode. And we achieve that by using the Zener diode 751. So that's the Zener diode that we are going to use to achieve voltage regulation. Then we can also use this as a voltage limiter to limit the amount of voltage, and you can use various types of diodes to achieve voltage limitation. I can use the diode to sense light. So this is the application of the photodiode or phototransistor. In this case, we are talking about the photodiode, and also produce light, which is the LED. So if you look at all the diodes, we've been talking about 4148, which is the most common one that we are going to use. Zener diode, LED, photodiode, they have a variety of applications. So, oh, I missed one more application. AC to DC. So voltage rectification. Rectification essentially means changing an AC voltage to a DC voltage. So that is also another application that we can achieve using a diode. Okay, so we talked about symbol purpose applications. Next, we will talk about the current voltage characteristics of the diode. However, before we talk about the current voltage characteristics of the diode, we are going to quickly remind ourselves of the IV characteristic of the resistor, and we can actually talk about the capacitor and inductor as well. So if you have a, say, a voltage source over here that you have connected to a resistor, and this is ground, say, and this is the AC voltage source. um, the value of this guy is R, for example. This is, say, whatever, V in, and there is some current I sub R flowing through this, and there is a V sub R voltage across the resistor. So we are indicating that there is a voltage source which is sinusoidal, or which is AC, so it changes with time, and we are calling that V in. As we change the voltage, obviously the voltage across the resistor is going to change, which means that the current through the resistor is also going to change. So if I were to sketch the IV characteristics of this particular resistor, so the resistor over here under investigation is that guy. So if I were to do that, how would the IV characteristic look like? Let's see, I will draw a graph here on which I will indicate that my x-axis is voltage across the resistor, my y-axis is current through the resistor. So what am I going to achieve for the resistor R? And this is 0, of course. So as I increase the voltage across the resistor, based on Ohm's law, for a value of R that is fixed, my current is going to increase in a linear fashion. So what I'm going to get is actually a line, straight line, that passes through the origin with a certain slope, and let's see what that slope is going to be. But it will be a line, because it's a linear relationship of what is the relationship? The relationship is VR equals IR multiplied by R itself. So based on that, we know that our slope of this line is going to be 1 over R. That's essentially what the current voltage characteristic of a resistor look like, a linear one. Now, if we talk about capacitor or even an inductor, those relationships were not linear. They were not as straightforward. So, just to get a sense of a comparison, we can say for the capacitor, the current through the capacitor was related to the voltage across the capacitor using the differential equation there, I equals C dV by dt. And for inductor, the voltage across the inductor was given by L di by dt. So two derivatives that are involved for the capacitor and inductor for their IV characteristic. Um, so these are the components that we have been looking at so far. Diode is going to be different. It's not going to be as straightforward. In fact, it's going to be a little bit of a challenge to write that form for the current voltage characteristic. To write it in a mathematical form, it's going to be a little bit of a challenge. So on this graph, on this slide, we have the current voltage IV characteristic of a diode. And the diode that we are considering is shown over here. So we have anode, cathode, the symbol over here, current only flowing in one direction as it is written over here. ID only goes from positive to negative terminal. And there is a sketch which shows how the voltage changes, the current changes as we change the voltage. So let me first talk about the circuit over here on the left, and then we'll go deeper into various regions in which the diode could operate. So over here on the left, we have another voltage source. This is again an AC source. We have two components in this in this circuit. We have a resistor of an arbitrary value here, 1K, and then we have a diode, the small signal diode 1N4148. Say we use the analog discovery scopes. channel 1 for the diode and channel 2 for the resistor. So what we are actually after is the voltage VD, right? Current voltage characteristic of the diode. So the component under investigation is the diode, and we need ID versus VD. So the question is, how do I know the voltage across the diode? Well, for that, we have used channel 1. But now the next question is, because that is measuring the voltage across the diode, 1 plus and 1 minus. But the next question is, how do I know what is the current that flows through the diode? Well, in this case, to measure the current through the diode, we have actually used a current sensing resistor, R1. So R1, the use of R1 in this circuit is for current sensing, because that is going to tell us how much current flows through the diode. And we are doing that by measuring the voltage across the diode, voltage across the resistor. So you measure VR1 using channel 2 of oscilloscope, and then you divide that by the value of R1, which is 1K. So if we do that, we are going to get IR1, and because the resistor R1 and diode D1 are in series, they should have the same current flowing through them. So that's how we are going to be able to measure the voltage and current through the diode simultaneously. And if we do all of that correctly, we should see a characteristic, IV characteristic, that is shown over here. Now several regions over here, as you can see. Let me pick some. The first region that we are going to talk about is the forward biased region. This is the region in which we have a positive voltage connected to the anode of the diode, and we have a negative voltage, or essentially it doesn't need to be negative and this one to be positive. All that is required is this has to be more than the cathode. So that particular region, we are going to call that forward biased region. And how do we achieve that in our circuit? Well, if you see over here, that's the positive end of the diode and it is connected to the AC source. So whenever the AC source has a voltage that is greater than 0, the diode is going to be forward biased. And in the forward biased region, you notice what happens. As I increase the voltage VD, the current is going to struggle to increase, but at some turn on voltage, it increases exponentially. So there is going to be, a period where the current doesn't increase. Theoretically, it is going to be 0, but then once I reach a particular turn on voltage in the forward biased region, it is going to increase dramatically at that point. But a key point over here is that particular voltage for diodes, it is going to be around 0.7 volts, positive 0.7 volts. However, can I achieve a voltage across the diode that is greater than 0.7 volts? So for example, can I get a 1 volt across the diode? Well, as you can see, you cannot get the voltage of 1 volt across the diode, which means that if my voltage source, the AC voltage source that I had over here, was sending was set to a 5 volt supply, then 0.7 volts would go across the diode, and the remaining 4.3 would go across the resistor R1, which is essentially going to be a current sensing resistor. So I can calculate the amount of current that goes through the diode, which means for that particular case, I can figure out where I am on the y-axis over here, because I'm going to be able to find ID. Okay, that's your forward biased region. Now, if you go into the reverse biased region, which means I have a lesser voltage on the positive side compared to the negative side, cathode. So that's we are going to call that region reverse biased region. In the reverse biased region, I have a very small amount of current called the saturation current, denoted by I sub S, flowing through the diode in the other direction, in the negative direction. But that is going to be of the order of nanoamps, so very small. Uh, Theoretically, zero. Um, but for a long time, as I go in the negative region, so say -1, -2, -3, all the way to about -100 for the small signal diode 4148, up till about -100, I can keep going, and it is going to be the same very small current that flows through the diode, and that's we are going to call that region reverse biased. So the reverse biased region is voltage across the diode is negative, anywhere between -100 to 0, if that diode is the 4148. It is slightly different when we talk about the Zener diode. More details to come in later. And what happens at the that -100 voltage? Well, if you increase that reverse bias voltage even further, the diode is going to break down, which means that now there is a lot of current that flows through the diode in the negative direction. So it's like where the dam breaks, there is going to be all the current that goes through in the other direction. Um, and as you know, -100 volts is too low. We will not be experimentally be able to explore this region for the 1N4148 diode. However, we will be able to explore it for the Zener diode. And the positive voltages, yeah, we can obviously get 0.7, no problem, from the analog discovery. So we wish we will be able to explore that positive regions without any trouble. But the negative ones are going to be an issue for the 1N4148. Let me highlight this region as well. This is called the reverse breakdown region. So as you can see, this is broken up into three regions: forward bias, reverse bias, and the reverse breakdown region. So all of them depend on the voltage across that diode. And if we know the voltage across the diode, we will be able to comment on how much current flows through it. Is it going to be very small? Is it going to increase exponentially on the positive side, or is it going to be increasing exponentially on the negative side? Okay, so these are some of the details regarding the current voltage characteristics of a diode, and as you can see clearly, these are very different from what we have been looking at for the resistor and capacitor and inductor. Okay, so at this point I can take a question. um, the question is: subtract the threshold of the diode from the circuit's voltage, then calculate the current in the circuit using the remaining voltage. Yes, that's exactly right. So the turn on voltage or the threshold voltage of your diode, if that is 0.7, that is going to be the case when it is one diode. Obviously, if you have more and more diodes over here, that is going to proportionately increase. So if there were two diodes over here, that would be 1.4 instead of 0.7. And whatever remains, because sum of voltages in the loop should be 0. So if I'm giving 5 volts here and two diodes take up 1.4, then I will have 3.6 volts remaining for R1, which will result in 3.6 milliamps that flows through R1. Another question is diode recoverable when a breakdown yeah, it is, but it takes a long time to come back. Compared to the switching which happens between the forward biased and the reverse biased, it's going to take a bit of time to come back from the reverse bias breakdown region. Yes, it is possible. Other questions? VD wouldn't necessarily be 0.7. Well, for all theoretical purposes, we are going to have to stick with some uh, value where everybody can agree that this is going to be the value where the valve turns on. So uh, that value for the diode is going to be 0.7 volts. So if you go a little bit more precision, like if you go zoom in and actually find out what that limiting voltage is, it might be 0.71, 0.72, and all those details you can explore, using the data sheet. um, but for the purposes of theory and equations, we are going to assume that it is 0.7. But yeah, it will be zero point 0.7. What I mean to say is we are not going to say 0.8 is a turn on voltage. If we have, say for example, we are giving 0.1 volts for the source. If I have 0.1 volt for the source, the diode is off and no current flows in the circuit. So it is going to require 0.7 volts from the source to turn on, and after that we can find out what the R1 is going to be. uh Previous page. George, are you talking about this page? The first one. All right, this guy. All right. Okay, so what I can do is we will solve a little problem so that we can uh, get familiar. Over here, we are doing a very simple exercise. We have a voltage source, Vs, and we have assumed that the Vs is voltage amplitude of this is 5. It's a sinusoid of frequency 1 kilohertz. So 5 sine 2 pi 1 kt. That's our AC sinusoidal voltage source. We have connected that to a resistor and a diode. We are measuring V out across the diode, and we are also interested in finding the peak ID, so peak current. Notice that this is a sinusoidal voltage source, so this ID will be changing. It will not be just one constant. So we are essentially trying to figure out what is the peak ID, which is going to correspond to the peak voltage of Vs. So let's try to see, well, actually let's do this. We'll try to sketch a Vs, V out, and we'll also sketch a voltage across the resistor in this case. So I'll start first with a axis, and let's say I have going to try my best here to um, okay, let's see, I am going to draw a sinusoid, a ref sketch of sinusoid. So let's say I have that. Um, so essentially, what I'm saying is the peak over here is 5, and the null over here corresponds to negative 5 volts. And on the x-axis, I have voltage in volts, and on the y-axis, I have time in seconds, for example. And because I assumed a voltage source which has a 1 kilohertz frequency, that means that my time period is going to be 1 millisecond. So I can say this is going to be 1 millisecond, this is going to be 0.5 millisecond if this is 0. So in black, I have Vs as a function of time. That's what my voltage source is providing to the circuit. The next thing I'm going to do is find out what V out is going to be. Well, V out, the property of V out is this. Let me draw V out in blue, for example. So for V out, I know that it is the voltage across the diode, which means that it can be uh, so as I increase the voltage, what is going to happen? It is going to start increasing 0, 0.1, 0.2, and so on. But beyond 0.7, it cannot go. So if I were to limit this, so for example, if I say this guy is 0.7 over here. So until that time, it is going to follow the source. And at that time, it will have a flat line because the voltage across the diode cannot increase beyond that. Notice this is a theoretical exercise. In practice, that might look like a slight curve over there. Next, as I decrease it from 0.7 to back to 0, it is going to follow the same way. And can I go negative? Absolutely I can. So as you can see over here, when I move the negative voltages of across the diode, I can explore them. Meaning, if I go negative here, I can see those negative voltages across the diode. So the blue line will keep following the source as it goes negative. And then back up over here, it will follow that, and then at 0.7, it will flat out. So in the blue, what we have is voltage across the diode. In this case, we are saying that's V out. Now the next question is, maybe I should make this a little bit thicker so that you guys can see uh, this a bit better, perhaps. That you can probably see. So the blue and the black are sort of on top of each other there. And then flat. Okay. The next thing is, let's say I also wanted to sketch the voltage across the resistor. Well, that is kind of very easy, right? Uh, because if I know Vs, then I also know voltage across the resistor and voltage across the diode, in this case V out. If I sum them up, I should get Vs, which means Vr should equal Vs minus V out. So if I were to subtract the blue line from the black line here, I should be able to draw VR. So let's do VR in red, for example. So between for the first few seconds where the voltage across the diode is rising from 0 to 0.7, it is going to the value is going to be 0 there, because they are going to both cancel out. And then as the voltage increases beyond 0.7, up until say that point, the voltage across the resistor is also going to change. It is also going to increase in the same manner. And then Again, it will do the same thing until that point there. So I'm essentially just subtracting the two lines and getting that. Now, as you might imagine, the differential here is going to be 0.7 volts. So if that guy is say 5, this is going to be 4.3 if that is 5 at the top. Next half cycle, they are both on top of each other, so Vs minus V out will result in 0. So that is quite okay here. That is all going to be 0. Let's see, all 0 there. In fact, all 0 even until there. And then we are going to again see that rise. Maybe that way is better. Right. So what we have in red is VR, again as a function of time. So I hope with this example you are able to see how the voltage across the diode is going to change, how the voltage across the resistor is going to change for a given voltage source Vs. So I'll take a moment here and see if you have any questions. We have done the V out, we have done VR. To answer peak ID, this particular question, we can use the voltage across the resistor. As you can see, voltage across the resistor, the maximum, the peak voltage across the resistor is going to be 4.3 volts right there, which means the peak current through the resistor, which is also the peak current through the diode, is going to be what is that, 4.3 divided by, we have a 1 kilo ohm resistor, so that's going to be 4.3 milliamps. Question is, will the voltage across the diode ever be anything other than 0.7? Well, it can be lower, right? So it can be 0.6, 0.5 and all that. In fact, it can go negative as well. But on the positive side, 0.7 is going to be a value for Zener diode and the small signal diode, which is the 1N4148. However, it is going to be different for example, light emitting diodes. For light emitting diodes, in fact, it depends on the color of the diode as well. So for example, and this I may be wrong with the numbers here, but the red LED usually requires about 1.6 volts to turn on. So that is going to be the turn on voltage for the LEDs. And green one probably requires like 2.3 volts to turn on. So it depends on the color of the LED as well. But that number of 0.7 is for the small signal diode 4148 and the Zener diode 1N751. Yes, it depends on the type. Okay, let's keep moving here. Um, so let's see what happens if we have um, a few more diodes in our circuit. So I'm going to draw an arbitrary circuit over here. Let's say I have a voltage source and I have a resistor here and I have two paths. Say on the positive side I have one, 2 diodes and 3 diodes, and on the negative side, or in another path, I have let's say one here and one here. This is my R. All of these are 1N4148. So all these are small signal diodes here. This is VS. We can use the same VS, like 5, whatever we had before. 5 sine 2 pi 1 kt in volts. And we of course need a ground here. So if this is our circuit, what is going to be measured over there? So right now we are measuring across multiple things. There are two parallel paths. In one parallel path, there are three diodes pointing down. On the other parallel path, there are two diodes pointing up. We are assuming the same Vs over here, and for this particular exercise, the value of R actually doesn't matter because we are only interested in sketching Vs and Vr. Vs and V out. So let's see what we can get over here. So quickly, I'm going to do that, followed by okay, sinusoid, just one period. This is again 5 sine 2 pi 1 kt, so frequency is still 1k. And if I was trying to measure V out, what should I get? This is time again, this is voltage. Well, I know that there are three voltages. So over here in the positive half cycle, these three guys are going to be forward biased and these two guys are going to be reverse biased, which means that as they are forward biased, each of them is going to take 0.7 volts across them to turn on. In total, 2.1 volts. So if I'm measuring V out on the positive side, it is going to limit, keyword limit, to 2.1 volts. So it's going to rise up and at 2.1 is going to flatten out. Same thing over here, 2.1 volts is going to flatten out. Now let's talk about what happens when there is a reverse cycle. When you have a reverse cycle or reverse biased, these three guys are going to be reverse biased, but these two guys are going to be forward biased because you have a negative towards a negative and positive towards the positive. And they are going to need in total 1.4 volts to turn on. That tells me that on the negative side, the voltage is going to be limited to 1.4. So using that, I can say this is going to be 2.1 and this is going to be negative 1.4 volts, where this is my V out. This is 0 again, and so on. Okay, so this is essentially what we talked about is voltage limiter. As you can see, we have limited the voltage on either side, positive and negative, by having appropriate number of diodes. So that's a voltage limiter. Okay, so let's see what else do we have here. Sorry, what I'm going to do is go to the experiment and then take a look at if there is anything else we need to talk about. So we talked about a simple resistor and diode in a circuit. Let's see what we are going to do experiment later on. Keep moving. Yeah. Okay, we can talk about half wave rectifier. So for a half wave rectifier, and we'll also talk about a full wave rectifier, for example. And we can actually do it over here. So a half wave rectifiers are circuits that are responsible to convert AC to DC. I'm going to highlight that over here. Convert AC current to a DC current. So something that keeps changing with time, I'm going to convert that to something that doesn't change with time. So essentially, if you think about, say, a rectifier here, what is the input, what is the output? Ideally, the input is changing with time and the output is going to be constant with respect to time. Both of them have time on the x-axis. So how can I use a diode to get rectification, that conversion from AC to DC? There are two choices. One is, the simpler one is half wave rectifier, and the other one is a little bit more complex, called the full wave rectifier. Obviously, with the half wave rectifier, my conversion is going to be not as good as the full wave rectifier. So what I mean by that is, the quality of rectification depends on how how much variation occurs in that output voltage. Is it going to be like that, or is it going to be like that? So this indicates a higher ripple voltage. This indicates a lower ripple voltage. This one indicates zero ripple voltage, which means that this is the ideal one. But we will be able to get these sort of graphs when we use half wave or full wave rectifier. So we'll take a look at these in just a bit. Um, what do we have here? We have a circuit. Let's see, I'm going to erase all of this uh, and get into a circuit here. um, Diode and resistor, the places have been exchanged, but they are still in series, so it really shouldn't matter um, what is happening. There's still, it requires 0.7 volts to turn on. All the remaining voltage goes to R2. We have a wave gen, so the AC voltage source, we are going to use wave gen to create that. We are going to measure wave gen over here and then connect it to a diode and resistor. So let's suppose for our wave gen, I will draw that in black. We have something like this, some AC voltage source with respect to time. The x-axis is time and the y-axis is again voltage. That's for wave gen. If that is the case, what is going to happen to the resistor R2? So on the other hand, we are measuring R2 on channel 2. So I'll use blue for that. I know that as the voltage increases, the diode is going to limit it to 0.7 on the positive side, and on the negative side, because there is just one diode here, on the negative side it is essentially going to follow the source. So for the resistor, if I measure just for the resistor, what do I get? Well, I will get something like this. I will get a I will start here, I will get a curve, and then I will have 0 for the negative, I will have another bump, and so on. Where have I seen this before? If this is the voltage and that I'm saying that's the voltage across the resistor R2 here, this is time. Where have I seen this before? This is exactly the same graph that we saw, I'm sorry, right there, right there. So that's the red, zero, and so on. What we did is just replace these two, the position, but they're still in series. So essentially the same circuit um, being observed in a slightly different order. So what do I get from that? Sorry, go back here. So what do I get from that? This is essentially what I did was I chopped off the negative cycles, right? So essentially I eliminated the negative half cycles of source. So essentially I've just removed these guys. But I've also reduced the peak voltage by 0.7. But that's a very small change. The big change is we have removed the negative half cycles of the voltage source. So that's a half wave rectifier, but it's still, remember, our goal is to get something like a DC, right? Like that. But we are not there yet. We have come to this place. So we have eliminated something going negative, but we have still some work to do. So what we can do is we can take this output voltage and put it through a resistor, sorry, capacitor. So we can actually put a capacitor right there, and we can charge the capacitor and discharge the capacitor. And if we are able to do that, essentially during the charge cycle, the capacitor goes up, charges to the maximum value, and doesn't discharge instantly. Instead, it will discharge slowly over here, charge again, discharge again, charge again, and so on. So by using a capacitor called smoothing capacitor, we are able to smooth out those positive half cycles into something that is sort of DC. You can see that it is still not flat. It is still not flat. It is still having some ripple, but it is getting very very close to flat. And by adjusting the capacitor value, if I have a really really big capacitor, then I can get a flatter output voltage. So that's your half wave rectifier. But another key thing over here is what is going to be the time, say over here, between that and that. Well, that depends on the frequency of this guy. So if the wave gen has a particular time period, that time period is going to be over there, right? So if I assume that this is the 1 kilohertz signal, then the distance between this guy and that guy is going to be 1 millisecond in time. So that will dictate 1 millisecond there. But that is useful for comparison, because in half wave rectifier, we essentially increase the frequency by a factor of 2, meaning we reduce the time period of this uh, output by a factor of 2, and we'll take a look at that in just a bit. So that's yours, half wave rectifier with a smoothing capacitor. Let's see, the circuit essentially looks like this. uh, So we have the diode, we have the resistor across which we are measuring, and then we have that C1, which is the uh, smoothing capacitor. Okay, let's see, come back here. Now let's talk about the full wave rectifier. Now for full wave rectifier, the story is a little different. So first of all, what am I going to do? I'm going to actually trace out how the forward biased regions and the reverse biased regions work out. So I will highlight using different colors. So for example, I'm going to use blue for what would happen, essentially what is the direction of flow of current when there is a positive voltage on this voltage source, AC voltage source. So what is going to happen when there are positive voltages? So I'm looking at positive voltages in blue. So I'm going to trace it using a blue highlighter. Uh, Positive voltages, the current is going to flow in this direction, is going to come over here, and I can only flow in one direction. Then I'm going to go through the load. Then I'm going to flow here. I'm going to flow in one direction back to the source. So the blue line essentially is tracing the direction of flow of current when there are positive voltages on the voltage supply. And as you can see, if so for those positive voltages on the AC voltage source, what is going to be the voltage across the load resistor over here? There are two diodes that are being used in forward biased region. Each of them requires 0.7 volts to turn on. In total, that is going to be 1.4 volts to turn on, meaning the remaining voltage will go across the load. So Vs minus 1.4 will go across the load for the positive half cycles. Now I'm going to use another color, perhaps maybe pink, for the negative voltages. So what I'm saying is, now for the negative voltages at the source, what is going to be the direction of flow of current? uh, I'm going to start here, negative. Actually, you know what, let's just erase this guy so that we can trace it a bit better. Negative voltages over here is going to use this path, go through the load resistor, come back out over here, go through this path, and there. And as you can see here, it is using the remaining two diodes. Again, the same deal, negative voltages minus 1.4 for the two diodes to turn on. Remaining, the whatever remains goes across the load resistor there. So in other words, I will be able to see the positive voltages, and I will also be able to see the negative voltages on the diode. So if I give it an input that looks like this, because I'm not eliminating any half cycle or positive or negative. I'm seeing both positive and negative on the output side. I'm going to take, with that configuration across the load resistor, I'm going to observe a waveform that looks like this. And then if I use this to charge my smoothing capacitor, then I will get a rectified and smoothed out voltage. Now, the only difference is this is going to be much better than the previous configuration of half-wave rectifier. And the reason is, earlier the distance between that and that was 1 millisecond for a voltage source of frequency 1 kilohertz. Now I have reduced that time period to one half. So I will require a much smaller capacitor to get the same ripple voltage. So that's how full wave rectifier is better to do that rectification for AC to DC. Okay, so and then this is the voltage limiter exercise that we already did. We talked about voltage limiters earlier. So I'm going to take a moment here to see if you have questions, and then we can start off with some experiments and some interesting things. Yeah, in terms of content, yeah, part C is a photodiode and phototransit. So in terms of content for part A and part B, I believe we have gained good ground. So for today, we'll focus on part A and part B of experiment 8. Um, in the time that remains, we will be doing experiments, we'll be launching MATLAB, and we'll try to explore the current voltage characteristic in MATLAB, and we'll try to fit a line to that. Uh, let's see. What did you say the period was reduced by a factor of each for rectifier circuits again? Okay, so let's see. For a half wave rectifier, let me put it over here. For half wave rectifier and full wave rectifier, right? What is the frequency of the source? Well, if I assume 1 kilohertz for both of them, frequency of the source, then the frequency, or I should say time between peaks, time TP, which is time between peaks, is going to be 1 millisecond here, because as you can see, whatever time period is there is going to be over there. So time between peaks is going to remain the same, 1 millisecond for half wave rectifier. But for full wave rectifier, time between peaks is going to go down by a factor of 2. So it's going to become 0.5 millisecond. So time period is becoming half. In other words, the frequency of that ripple is going to double. So more frequent ripple. So, and that is illustrated on the next line over here, as you can see over there, because it's now getting both of them, positive as well as negative half cycles. All right, so let's me where is my mouse? Right there. Let me stop the recording here.